Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of transformations of functions. You should have already watched the video on how to shift functions vertically or horizontally. You should have watched my video on how to reflect graphs about the horizontal or vertical axes. You should have also watched the video on vertical and horizontal stretches and compressions. There's also another video on odd and even functions, which can be very important, and I will likely include that as part of our conversation here. So let's talk about doing all that at once. Performing a sequence of transformations is actually what you're going to be doing for the most part in your pre-calculus course, and also you're expected to kind of know what a function looks like after performing a lot of transformations in your calculus course. However, I will be very honest with you. It's not that in calculus somebody says, hey, here's a function that's a transformation of a base function. Please graph that function. It rarely occurs like that. However, the natural knowledge of what a function looks like based upon transformations is very important, so that you know whether your function is opening up, opening down, whether it has zeros, all that fun stuff. So let's talk about this. Let's suppose I give you a function, and you can ignore my G and F thing here. It's just really that you're handed a function. So down below, I'm going to do an example here. So for example, let's suppose that you're handed a function f of x, and somebody just handed it to you like this. Let's say it's a -7 minus 2/3 times the absolute value of, I don't know, let's say 2x minus, let's say plus 4. So somebody hands you that function, they ask you to graph that function. The very first thing I highly recommend you do is rewrite the function in a different order. That is, rewrite it to where the base function goes first. And when I say the base function here, you should already know the base for this function is the absolute value of x. So I'd like that absolute value to be written, that term that involves the absolute value, that is, to be written first. So what I'm going to do is go ahead and say this implies that f of x is actually equal to a -2/3 times the absolute value of 2x plus 4, and absolute value and a -7. Now, something that is special to this specific function is that you technically could factor a 2 out of the interior or the argument of that absolute value. You can factor a 2 off of both those and pull it out front. I'm not going to do that here, mainly because that's only the case with this absolute value that you could do that. If this was, for example, a square or a square root or a cubed root or some other function like that, it's often not easy to just factor outside of the function. So let's keep all the numbers inside the function inside, and all the numbers outside the function outside. Let's just stick with that rule. Since you've watched a prerequisite video, I just want to say this, that a lot of students will say, oh yeah, that right there, oops, except that wasn't supposed to be a highlighter. They'll say, this right here means that we have a horizontal shift. There are two mistakes that are usually made here. The very first one, and this is in red because this is a mistake, okay? So what I'm writing here purposefully in red is me telling you intentionally, do not do what I'm about to say. A lot of students will say, this is a shift to the right by 4 units, and it's not. So I'm going to say not. It's not a shift to the right by 4 units. Now, then if somebody looks at that and they say, well, of course it's not a shift to the right by 4 units, because that plus means you're going to move to the left. It's always the opposite of what you think. So it's shift to the left by 4 units. Again, that's not true either. So why isn't that true? It's because of what I just mentioned a moment ago. There's an illusion. There's something hidden here, and you're not actually seeing the true horizontal shift. And so when I scroll back up here and I go to this second piece of advice, if your coefficient of x, and I'll put this right here, I'll just say coefficient of x, if that is not 1, then you must factor that coefficient off of x. So the function g is still hanging out there. In our case, the function's called the absolute value, not g, but whatever. And you're going to factor that b off of x, but you also factor it off of this c as well. So the b gets pulled out and the c gets pulled, and the b gets pulled out off of the constant as well. So it gets factored off the variable term, the x term, and it gets factored off the constant as well. Remember, factoring is division, so that's basically what we're doing here. We're dividing both of these terms by b when we factor by b. The reason why you do that is so you can see the actual shift. So let's go ahead and do that in our sample case down here. So I'm going to go ahead and factor. I'll use black ink just to say, okay, this is what was here before. And then I'll use green ink to showcase that I'm factoring something off of this. So if I divide that 2x by 2, and if I divide the 4 by 2, there you go. Oops, I don't want green ink there. I want the rest to be black ink because I didn't actually touch the rest of this. So that's all. Now, in this case, you would be absolutely correct in saying, in fact, let me use green, saying that's good. You would be absolutely correct in saying that's a shift left 2 units. Notice it's not a shift left 4 units or to the right 4 units. It is a shift left 2 units. So it's critical. Otherwise, your graph is completely wrong. That being said, so that's the only real tricky part here. The rest of this is just graph the base function without transformations and then apply, reading from left to right here, apply each transformation in subsequent graphs. Now, your instructor might not require you to do that, but I do. The reason why is it's terribly easy for people to just go to Desmos, figure out what the graph looks like, and copy it. I don't want that. I want to see that you know what transformations do. I want to see every little step. And when you do this, critical to note, you don't need to be super like crazy awesomely accurate. You don't need to use graph paper from the get-go. All you need to do is quickly sketch out. I call it a sketch when I'm not really focusing on idealized graphs here. I quickly sketch out the absolute value function, which is a base graph, and you plot 2 points. Notice I didn't graph that by plotting points. Instead, I graphed it first and then I labeled 2 points on there. So graph, then label. If you plot a bunch of points to connect the dots, it will be incredibly obvious. In fact, I have just graded an assignment for one of my courses, and this is for a, I think it was for a trig course, but within that course, they were graphing piecewise defined functions. And you could tell the people who were just listing out a bunch of points and connect them with dots because their graphs were terrible. And so they just get 0. So you do not want to graph by plotting points. You'll get a very incorrect idea of what your graph looks like. All right, so going from left to right here, I'll now focus on that guy. And I'm not going to write out each and every little step, what it's doing. I'm just going to show what it's doing. So applying the negative, so y equals a negative absolute value of x, that just flips this graph upside down. Again, I could label these very quickly, right? The y values are just the negative of what they used to be. And then I go ahead and move on to the next one, 2/3. So I'm just going to map down a little bit here. Now, multiplying by 2/3 just means the y values are 2/3 of what they used to be. Well, they used to be 0, 0, or in other words, the y values were 0 and -1 here. Well, 2/3 of 0 is still 0. 2/3 of -1 is a -2/3. So it's a little bit what most people would call wider. That's what it looks like. And if you watch my previous video, you know that's an optical illusion. But there you go. Notice I'm still not being super, super crazy accurate with this. I'm just quickly sketching here, each step along the way. The next move, oh, I didn't have to zoom out that far. The next move is to talk about that 2 on the inside, that green 2 on the inside. What that's going to do is multiply each x value by 1/2. So instead of going through x equals 0, it'll go through x equals 0, because 0 times 1/2 is 0. But instead of going through 1, -2/3, it's going to go through 1/2, -2/3. So maybe something like this. People say that that looks narrower. It does look narrower. It's not. But that's 1/2, -2/3. Now the rest of it's actually pretty simple. It's just moving left, right, up, or down. But I do want to mention something here. If me multiplying the x values by 1/2 confused you, please watch the prerequisite video, which is the vertical and horizontal stretches and compressions. I explain why that is not a multiplication by 2. It doesn't stretch the x values by a factor of 2. It actually compresses them by a factor of 1/2. And now we'll shift left 2 units. Some people do this last bit all at once, by the way, and that's perfectly fine. If we shift left 2 units, then our point here will be at -2, 0. And our point here will be, well, 1/2 minus 2 is a -3/2. And then we're at a height of -2/3. That's supposed to be a negative. And otherwise, I'll just connect that dot. It's symmetric, so I don't really have to super worry about that. And then finally, I'm going to shift this down 7 units. And I'll have my final graph. And when I do that, I actually go ahead and try to be a little bit more accurate here by labeling things appropriately. So I'm over 2 units in the x direction and down 1, 2, 3, 4, 5, 6, and 7. So that's -7 right there. That's a -2. I know the vertex or the anchor point is right there. The anchor point is really the point that was at 0, 0. That's what I call the anchor point. And this is now at -2, -7. You have to label these points. It's very critical. And you have to label that other anchor point, which is at -3/2, somewhere right around here. This is, I say right here, right about there. That's the x value of -3/2. And the y value, well, it was at -2/3, and you're going to lose 7, which is losing 21/3. So losing 21/3, and you have another 2/3 you're dropping, that'll be a -23/3. So I'm going to put it right around here, maybe. And that will be a -3/2, -23/3. Just a little bit of arithmetic there, and then you connect them up as nicely as you can. Put a little arrow there, meaning that that goes on down forever. I don't actually label the other point on the other side. I just do that. That is a very good graph, although that 2 is bothering me, so I'm going to erase that 2 and just rewrite it as a 2. There we go. And that's the graph of that completely made up function. I just wanted to showcase the idea. All right, so let's go ahead and try this again with a completely different function. You can see right here, I have actually, this is a fairly typical style of function you'll see. And by the way, this is written already in the proper order, right? The function itself, the base here is y equals x squared. And notice the term that has the x squared there, that goes first. So that is perfectly fine, well written. And I'll just chicken scratch out very quickly what x squared looks like. I happen to know it goes through 0, 0, 1, 1. I'm not really super concerned about that right now. And then I will go ahead and graph y equals a negative x squared. And that's just the upside down parabola. It goes through 0, 0, and 1, comma, negative 1. Now notice once I step away from the original base graph, that's when I start kind of labeling things. Now we're going to multiply the y values by 3. By the way, you can combine, it's totally fine to combine these first two into a single move, right? Where you can say, well, I'm just multiplying all y values by a negative 3. That's perfectly okay. I would not mark you off for doing that if I was your instructor. So let's go ahead and multiply the y values by 3. Kind of like this. I'm messy. That's fine. It still goes through 0, 0. And this is 1, comma, negative 3. I'm not being super accurate because I know my final graph is what I'm going to be judged on. However, I know my instructor wants to see all these little steps in between. And now the next piece, which I kind of forgot to do, but that's okay. I could do it right now that I've caught up to this, is that I could say, well, our original function is negative 3 times something squared plus 1. That something, I'm going to have to factor a 2 off of that x there and also off the 1 so I can see the actual shift, because a lot of people, again, will think this is shifted to the right 1 unit. It's not. Factoring a 2 off, you can see it's actually shifted to the right 1/2 of a unit. And that's critical. So let's go ahead, because we've already done the vertical reflection. We've already done the vertical stretch. Now I'm going to do the horizontal compression. Remember, that's a compression by a factor of 1/2. So I'll write that down below here. All the x values get multiplied by 1/2. So again, it still goes through 0, 0. I'm not going to mark that. But this x value, which was 1, is now 1/2. And the y value is still negative 3 there. And now I get to do the easy parts, which are basically the horizontal and vertical shifts. And I'll do those all at once because I want to. This right here, and you should be allowed to do that too. Really, the main thing is you could do this in only 3 panels. The first panel being multiplying all the y values of the base function by a negative 3. The second panel being multiplying the x values by the reciprocal of that. So it'd be 1/2. And then the final panel would be your shift horizontally and vertically. So you could do it in 3 panels, honestly. So let's go ahead and just do this last panel. I'm going to shift, let's see, that's to the right 1/2, and this is up 1. I guess I could have put the P there, right? It's the same amount of writing. So I'm going to go ahead and try to be somewhat accurate here. Here's my x-axis. Here's my y-axis. Let's see. This anchor point right there was at 0, 0. It's no longer at 0, 0. It's shifted to the right 1/2 a unit. So I'm going to call this x equals 1 so that I know that 1/2 a unit is right there. And it's lifted up 1 unit. So something like this. That's my new anchor point at 1/2, comma 1. I also know that this other point was also shifted to the right 1 unit. So now it's at 1. And the x value is, that is. And the y value has been shifted up by 1 unit, which means the y value is at negative 2. So I will label that point 1, comma, negative 2. Again, you're just shifting everything to the right. So you add 1/2, because you're shifting everything to the right 1/2 units. You add 1/2 to the x value, and you're shifting up by 1 unit. So that y value becomes a negative 2. You can actually just connect these points. And this is where I think it is kind of critical to remember this is an even function. It shouldn't be bowing like that. And I mentioned it, I think, in the previous video, but if I didn't, then I'm just going to say it out loud here. I do a lot of kind of work like this where I'm shading quite a bit because I'm trying to make it look smooth and accurate, even though it might not be. Now, because this is an even function, because it's x squared, I know it's symmetric about the original y-axis. Now my y-axis, or I guess my axis of symmetry is what we'd call it, is no longer the y-axis. It's this vertical line right here. So it's symmetric about that vertical line. So this distance here is a half, so the distance here should be a half. So I know that it's also going to go through this point. And so I will go ahead, try to connect those appropriately. It takes a little bit of work to do that, but you can see actually I did a decent job. Also note at the top, this is not supposed to be pointy. It's supposed to be rounded. So notice I spend a little bit of time rounding that out just because I want my instructor to know, and I want you to know, that that is a rounded top edge, not a pointy top edge. And there you go. That is the graph of f of x, which is -3 times the quantity 2x minus 1 and quantity squared, then plus 1. Beautiful graph. If you were wondering what I meant when I said axis of symmetry, that's actually from Algebra 2, but it just basically means that when you have a symmetric function about the y-axis, so for example, this right here, you can see that's a rotation about the y-axis, because it's an even function, then really I didn't need to graph the entire parabola all along. I could have just spent my entire time graphing only the right half of that parabola, and I would flip the right half of the parabola, hold on a second, and then I would stretch the right half of the parabola there. So you could totally graph it this way. And then I would, what is this? Oh, this is the horizontal compression. So I would have a horizontal compression of the, again, right half of the parabola. And then once I was ready, I would initially graph the right half of this. And then I would say, great, I know the rest of it is just symmetric about the vertex, about where the vertical line here has been shifted. Since that vertical line has been shifted to the right 1/2 units, because everything was shifted to the right 1/2 units, I know that my mirror, my axis of symmetry, is this vertical line shifted to the right from the y-axis 1/2 units. And so I could then copy my graph that is the right-hand side over to the left-hand side here using that axis of symmetry. So maybe I'll see if the next example offers us that opportunity, and that's the way I'll graph the next example. I think it actually does. I'm just checking on my main computer. Yes, it does. And actually on my main computer, that next example is an absolute value. I'm going to change it. All right, so in this next example, I actually adjusted it quite a bit, actually. This was originally an absolute value, and I think that it would be better to see it this way. So if you look at the base function of this, peel away the -2, the 3, the -4, and the 16, that is just going to be y equals 1 over x. That's the base graph that we're dealing with. And I want you to note that if that were, let's see, this function is called g of x, so let's call the base graph, let's actually call that b of x for base graph. Okay. Notice that if you were to plug a negative in there, negative x, or the opposite of x, you'd get 1 over the opposite of x, which is the opposite of 1 over x, which is the opposite of your original base graph. That implies that this graph, the base graph that is, 1 over x, is odd. We're going to use that fact here. You don't have to, but I just want to showcase kind of the things you can do. By the way, if that threw you off, please watch the prerequisite video on graphing even and odd functions. Actually, it's not graphing, it's just determining whether a function is even or odd. Because that's a critical skill, really important for calculus. Very, very important for calculus. But nobody ever tells you when you're in algebra why you have to worry about functions being even and odd. They just say, hey, this is what an even function is and this is what an odd function is. But they don't bother telling you why that's important. Well, here's where it happens. I happen to know that 1 over x, and as well you should know, looks like this. Notice that if you stuck a pin in the origin and rotated everything 180 degrees, it would be the same picture. That's the graphical view of an odd function. So if I know my function's odd, then I'm only going to worry about the right branch of this, because I know that in the end, all I need to do is take that pin that was in the center and rotate it around 180 degrees, and I will have my other part of the graph. So this just reduces the amount of work. There is something kind of important though to note here, and I didn't mean to erase that. Technically speaking, this point 1, 1 is definitely on the graph of 1 over x, but 0, 0 is not. However, I'm still going to use 0, 0 as an anchor point, and I'm still going to use 1, 1 as an anchor point for my graphing process, and you'll see why as we continue. So here's my function, g of x equals a mess. Notice this has a 3 in front of it, and I highly recommend, actually with these fraction or what we call the reciprocal functions, I recommend factoring the numerator off and what we've been doing, which is the lead coefficient of the denominator. Factor that off as well. Remember, you want x to have a unit coefficient. This is the one case where it is kind of important to go ahead and factor off the lead coefficient of x outside of the function itself. So what does this look like? Well, that's a 3 over a negative 4. And what happens with the rest of it? Well, the numerator becomes 1, obviously. If you divide negative 4x by negative 4, it becomes just a regular old x. If you divide 16 by negative 4, well, you get that. You guys should be okay with that. And then the minus 2 is just hanging out back. And this tells us the actual shifts, right? We see there's a vertical shift of negative 2 and a horizontal shift of 4 units to the right. I'll again explain that in a moment, but let's go ahead and deal with this. I said in the last example that you could take it in terms of one panel being your vertical reflection and stretch or compression. In fact, let me show that. In the last example, I said you could just have done all your graphing in 3 panels. The first one being the vertical reflection possibly, and vertical stretch or compression possibly. And then the next panel would be your horizontal reflection or your horizontal stretch or compression. And then the final set of panel, or the final panel I should say, would just be all of your shifts. The rigid shifts is what we'd call those, or rigid transformations. So going back here, I'm going to start with a panel just dedicated to this transformation. I will reflect the original function about the x-axis, and then I will shrink the y values by 3/4. So I will do that right here. I know it's going to be a reflection about the x-axis. All I did was flip across this because it's a negative 3/4. And then the y value is no longer at 1, it's at, well, 1 times the negative 3/4. There you go. Otherwise, 0, 0 is still my anchor point, and so is 1 comma negative 3/4 now. So that's done. There are no horizontal stretches or compressions here because we factored it out. which is another conversation in and of itself. So let's go ahead and just deal with the final panel, which are all the shifts. So let me do that. We have this shift and that shift. Remember, the shift with the x minus 4 moves the graph 4 units to the right. All the x values, you're going to add 4 to them. And this, all the y values, you're going to lose 2. So I'll say minus 2 from, that's kind of big ink. Let me zoom out a little bit. So minus 2 from y values. And then the other one is add 4 to x values. Here's my guide. So I'll take those 2 anchor points and I'll add 4 to their x values and subtract 2 from their y values to get my final graph. That was very quick, right? So that anchor point at 0, 0 is now at 4, negative 2. 1, 2, 3, 4. 1, 2. Now I'm not going to label that. There's a very specific reason. Whoops. And then the other point, which is at 1, negative 3/4, well, I add 4 to its x value, so it's at 5. And I subtract 2 from its y value, so it's at negative 2 3/4, which is, what is that, negative 11/4. So I'm going to mark this as negative 1, negative 2. I think that looks right. I have to stand over this. And negative 3. But negative 2 3/4 is not exactly to 3, so I'm going to plot it right here. I am going to label this point because it actually occurs on my curve. That is 5, negative 11/4. Don't use mixed numbers in anything beyond arithmetic. Mixed numbers are great for cooking and carpentry. They're not really good for anything else. I'm sure you can create some example where they are good for, but let's just pretend as though they're not good for anything else. Now, I told you that we're not going to label this anchor point right here. The reason why is that original anchor point with the reciprocal functions, you should know that anchor point was a good guideline for the center. It's like the target, or better yet, the crosshairs for your asymptotes, for your vertical and horizontal asymptotes for the reciprocal curve. So I'm just going to draw a horizontal asymptote here. And I tend to, I've mentioned in the past, I tend to like to use green for my horizontal asymptotes, but I just have the red pen out, so I'm just doing that. So totally okay. And you can see my screen's wiggling. I'm going to pause. And there you have our guidelines for graphing. Now all I need to do is actually just draw the curve. It's not going to want to touch the vertical asymptotes at all, or the vertical asymptote, I should say, at all. Just to let you know, it is actually okay in general for functions to cross or touch their horizontal asymptotes, but this one will not. So you don't have to worry about that. Now, we know that this is not the actual answer because, or the actual graph, I should say, because the original base graph was not just that right branch. It rotates around the origin, in that case, to create the other branch. Well, we're not going to rotate this curve about the origin. Instead, we're going to rotate it about the crosshairs there. We're going to rotate it by 180 degrees to get our other branch of this curve. So I'll go ahead and do that. If you're required to label 2 points, then just note that the x value moved from the vertical asymptote here, which is at x equals 4, over 1 unit to x equals 5. And therefore, the point that's the symmetric point that's on the other branch is 1 unit away from the vertical asymptote. The other thing you should note is that the y value of this point is 3/4 away from the horizontal asymptote. So the y value of the other point will be 3/4 away from the horizontal asymptote. There's a lot of symmetry going on here. So this point, if you're asked to graph this, which I tend to not ask my students to actually plot that point, but you are supposed to graph the actual curve on that side. But if you're asked to label that point as well, that's how you do it. You know the wiggle on one side to this point is 1 in the x direction, so it'll be wiggled by 1 in the x direction this way. You also know that the y value is wiggled 3/4 in this direction, so again, the y value will be 3/4 up. Well, if that's 2, -2 that is, -2 plus 3/4 is -1.5 or -5/4. Otherwise, this beautiful curve, it's not going to touch the horizontal asymptote, nor is it going to touch the vertical asymptote, and that is a really good graph of that function. And I should actually show the entire function in the picture. Now, I do like to kind of give extra examples here, especially for graphing. You should have been graphing at least for 2 to 3 courses now, so this should be old hat to you, but notoriously, people are bad at graphing. So I want to draw your attention to one final kind of trick to all of these. And that is to note what actually is happening with that horizontal shift. If you look at the function here, the original function we started with, the absolute value one, you can actually find the horizontal shift without doing the factoring. You could just say, what would turn, I don't want to use the lipstick colored highlighter, I'll use this highlighter. What would turn that into 0? Well, the thing that would turn that statement, that highlighted statement, into 0 is x equals a -2. And so that tells me that that's where it's been shifted 2 units in the negative direction along the x-axis. And if you look at that, shifted left 2 units. So that is a cool little trick that you can use. You're just asking, when is the argument 0? That's where it has been shifted in the horizontal direction. Look at the next example and try the same thing out. Well, remember the next example, this example right here, we said it shifted to the right 1/2 units. Well, let's use that little trick here. Let's take a look. If you want to know when that argument of the squaring function turns into 0, well, that turns into 0 if you add 1 divide by 2 at x equals 1/2. And so now I know that tells me it's been shifted right 1/2 units. So that's a really cool trick. And finally, if you take a look at this last example we did, and you're looking at this function and you're like, oh man, I don't know what to do, whatever, you know, like the reality is you could just have said this -4x plus 16 is, instead of 1 over x, it's 1 over that picture. When is that picture 0? Well, that picture is 0 at 4. And so therefore, this graph has been shifted right 4 units, and you better believe it, 4 units right. So that's the little trick that I think is very beneficial to use. Remember, I could do a ton of different examples, but the reality is if you don't get it now, then you really do need to go back and review very core material to graphing, because I've done 3 graphs here and then maybe several graphs in previous lectures. You have an infinite number of graphs essentially available to you in other video systems. But I hope that this clarifies at least a little bit of how things work.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.